pass on. Sorry, I hate chairman to get out of time like I'm doing, but it seems a pity to stop the discussion. This is what it's all about, isn't it? So if we could ask ditlevsen. Good, fine. Lovely. So instead of we forego the red line rather tomorrow.
Are we going to use some cookies? I think so. I didn't bring my laptop. I never do. I think I'm going to
Can you take the screen off and use the background?
Oh yes.
Den er elektrisk.
Den er også
Det kræver det store kørekort.
Ja, den der sådan men det er da bedre end de der fjernbetjeningsting, hvor alle knapperne i.
So what I thought I'd be talking about is just a very brief introduction to the problem of the climate and stabilizing the climate for conditions of life. And one thing that is sort of striking to me is this obvious fact that liquid water is necessary, and liquid water has been present on Earth for a very, very long time. And that is the reason for that is of course discussed, and it's not very obvious that it's been like that for this long. And another fact that I don't know if it's interesting is that water is actually the only substance that I know of which exists in its three phases, which is also kind of interesting. But the problem of having the liquid water for such a long time is that probably the sun hasn't been shining with the same intensity as it is today for as long as the Earth has been around. And we know from the data that the rocks that Minik, who will be here tomorrow, will present from Israel and Greenland, that we have actually life dated back almost to the beginning of the planet. Now, if it is such that the sun has been shining less in the past, in the beginning, we have this, which has been named the weak sun paradox, which is probably not a paradox, but the issue is that the temperature with the solar radiation being only about 60–70% of what it is today, in the early history of the Earth, water should be frozen. And water should be frozen actually up to maybe 2 billion years ago. And that, we know from geological evidence, is not the case. So we have had, so what I'm flashing here is the equilibrium temperature on Earth, and I'll return to that, and the equilibrium temperature of Earth with the greenhouse effect on top of it, calculated from radiative convective models of the climate and so on. So there are factors inside the Earth which makes the climate more habitable than it would be from an economic point of view, just looking from the distance from the sun and the external factors like that. And in order to get into that, I'd like to sort of present the most simple climate model that could be very helpful.
Can I just ask a clarifying question?
Sure.
The sun shined 11% less 4.5 billion years ago than today. Is that really enough to cool down the Earth so much that you can expect water to be freezing?
Let's see now here. This is new fact. These things for casting, that time they talked about 40% less, 34% less radiation from the sun. I'm not in that strong, I don't want to discuss that.
I think
you're saying that this is not true.
No,
but anyway, if it's enough, it's easy to see that you don't need to go too much from the present value here. So this is about, I would say this is probably half this would probably be something like 15%, not 11%, so we'd be pretty close to freezing at that point. Now, the problem is, of course, the following. We have a balance of the incoming radiation from the sun and the outgoing radiation just from the black body radiation on Earth. that we should be able to calculate which would be sort of the band of Earth-like planets around any given star, and what would then, chemistry being okay, be suitable living conditions for life. However, it seems that some sort of regulation in Earth, in the Earth system, has made it helpful for a longer time. And the most simple climate model for that would be, of course, to see these balances here does depend on what's going on in the atmosphere of the Earth. So let me just write the simplest model, which is due to Cells and Bedico in the late 60s. Are you all familiar with these kind of climate models? No? Then that's nice. That you do simple and from the basis. Basically, what we're interested in would be the temperature, some mean temperature of the surface of the Earth. Now, of course, this has to be governed by a balance between the incoming and the outgoing radiation. So having some sort of heat capacity of the system change, or this one here, would be the imbalance between the incoming and the outgoing radiation like that. This is sort of the most simple way you could look at the climate system in itself. So the whole issue is then, of course, to say what is the incoming and what's the outgoing radiation. Now, the incoming radiation is actually very different between the Earth, Venus, and Mars, even though we're pretty much in the vicinity of, say, this almost same distance to the Sun. The reason being that the reflectivity of the atmosphere is very different. Now, Venus reflects most of its radiation from the Sun. So the factor coming in here, which is basically saying that from the incoming part, which goes to the ground, a large part is just reflected back without heating the atmosphere or without heating Earth. This factor here is called the albedo, alpha here, which really doesn't contribute anything. So what we get in is the confidence on the solar constant minus this albedo factor here. Now it seems to be a trivial factor, but it's not, because this thing here will of course depend on cloud cover, ice cover, maybe on biology and things like that. So until now, let's just write that as some function of temperature. Albedo is a function of temperature. Now the outgoing radiation is just, I mean, in first function would just be something like Stephen Boltzmann law, like that. But we know, of course, that long-wave radiation is trapped by greenhouse gases and everything. So there would be some sort of factor just write as a gray in this factor here, which would also depend on temperature here. So these two factors we can now start playing around with very simply by just making sort of a plot of the balance between the two. If we look at this albedo factor here, and let me just do sort of classical way, and we can discuss in a while about how biology ethics would get into this. But let's just take a very simple situation that we have an ice cover here, somewhere up here, and ice has a larger albedo, it's white, so it reflects more light out, which we know. I mean, if in wintertime, if the snow covers the land, it will immediately be colder just from that reflection. Yeah. So basically, as a function of temperature, we know that for a completely ice cover, say temperature below some. Now we're talking mean temperature of the Earth. So let's just say 0 degrees Celsius here. We have some high albedo. So what I'm plotting here would be 1 minus alpha. So I have some low value here. For a high temperature, say it's a mean of 30 degrees or something like that, there'll be no more ice, we'll have some large value of 1 minus alpha, right? So these are things, of course, just to connect in some manner that we don't know. This would be the incoming radiation. The outgoing radiation, I mean, basically, this would be some sort of almost linear function. And this Green's factor here, we basically don't know the precise shape of this, but the point is that this would, of course, be an increasing function of temperature. Be an increasing function, it's just the black body radiation from our radiation from Earth. So we have some sort of curve up there, like that.
We have no Green's factor if your outgoing R is energy. I mean, then when you have the secret and the secret that is energy. So the only thing you have on your G, that is a distribution as function of wavelength.
Sure.
There has to be
because I mean, basically, you're right. However, this temperature here, I didn't really specify for you what this temperature is. If this is ground temperature, it's not really a from ground temperature. It will be from some temperature of an effective temperature for the outgoing radiation, like that.
Yeah, that's exactly the this is defined as the effective temperature, right? And that means that the G is 1. You cannot go up with G.
I'm not saying this is the effective temperature. If I define this as being temperature of the surface of the Earth, right? Then of course the effective temperature is some different. Let's just take Lucas' point here and see what goes on in the atmosphere. Is of course the following: we have an atmosphere which is clear with respect to visible light. Of course, that's why we got our eyes selecting exactly that thing. So basically, we are heating up the surface of the Earth by the short-wave radiation. Now, for the long-wave radiation, the atmosphere is opaque, right? So if we sit here with the eye in the eye, we cannot see the ground in the infrared, which means that basically we're seeing radiation coming from a level here, which is the level of the temperature, the effective temperature. Now, of course, the balance we need here is basically that the incoming heating should balance the outgoing sigma T effective to 4, right? Now this balance here we could easily get if we knew the albedo and so on and the solar radiation. So that gives us an effective temperature. Okay, this effective temperature is the temperature exactly this point up in the atmosphere. So if I plot now here as a function of height in the atmosphere, I plot the temperature here. I have at this level here, so basically, this is the same. Okay, let me just put it over here. It's more paradoxic. Okay, this is height here, this is temperature there. Now, the effective temperature here is the effective, is just what comes from this balance here. Okay. However, we know that the structure of the atmosphere is such that temperature increase with height, basically just for adiabatically moving, decrease with height. I expand particle of air, so it cools, and basically in the troposphere at least we have a temperature profile like that. Okay? Which means that here temperature of ground is larger than the effective temperature. This is the greenhouse effect. Delta T here, this is the greenhouse effect, which is 30 degrees present value. Now, basically, if the dynamics of the atmosphere changes, I might change this slope here is called the lapse rate. Now, if I change the lapse rate for some dynamical feedback in the climate system, I might have a different slope here. Now, from energy, these energy balance considerations, this needs to be the same. So I'm increasing the greenhouse effect here. Now the greenhouse effect, as we see it today, by increasing greenhouse gases, basically this is just making the atmosphere more opaque. When it gets more opaque, the effective level of radiation rises here. I can see less further down in the atmosphere. So basically I get to H1 here, and basically this temperature here needs to be the effective temperature in order to make this balance, and I get an increased greenhouse effect down here. This is sort of the IPCC type of greenhouse effect. Now, so this temperature here, basically in this simple model, you just have to think that this is the ground temperature, and this greatest factor here is really what counts for the greenhouse effect, right? Or whatever would change the lapse rate or something like that. Okay. So now the model is basically there, and we know now how this will behave, because this thing here has, of course, fixed points where these two curves they cross, which is here, there, and it's easy to see that below this point here, the incoming is larger than the outgoing, so it heats. So basically, this is a stable fixed point, this is an unstable fixed point, and this again is a stable fixed point, right? So if we, as we like to do as physicists, write this as an effective T see an effective potential. We just integrate this difference here, and what we end up with would be a potential like this, right? So basically, this kind of model would have two stable climates here, cold climate and a warm climate, and an unstable situation like that. Okay, so now of course this would, in short terms, explain why this is a stable point like that. Actually, the reason this model is interesting is that we also do have this evidence. I mean, basically, this thing here, saying that real life, interesting eukaryotic or multicellular life, actually didn't start until some 60 million years ago. Before then, life was only bacteria. And of course, as I understand, bacteria is only very complicated and so on. But going to funny life like our cells and dinosaurs and things like that took a long time. Now, we don't know if that is due to the fact that bacteria need to be around to gain experience for such a long period before it evolved in multicellular life. The possibility is that actually the title of my talk wasn't completely true. That climate was not that stable on Earth. Now there's evidence that a few times around 600 million years ago, or 700 million years ago, there are sediments looking like this. This thing here, which is actually the, I thought I had to flash something, so here's a picture here, this one here. So, this is one of the big discoveries of the 1840s. That was the golden age of natural history. First of all, and dinosaur bones were found. And this rock was found. Because people look rocks were around, but nobody asked the very good question of why? Who put this rock there? And this was not the giants throwing rocks. And there's this Swiss geologist, I see his name was. Because the only way this rock is actually in Scotland. It's a drawing from Scotland. The only way it could get there was that it was moved there by ice. Okay. So Scotland was at some point covered in ice, which we of course know now as a fact that we had glaciations. Now the glaciations that led to this thing here was not nearly as severe as the glaciations that have been seen to have occurred 700 million years ago. Because this period is evidenced by marine sediments in even tropical, at that time tropical regions. So this was a global glaciation. So basically, what had happened at that time could be the following. Now this has been dotted dramatically. Snowball Earth. Snowball Earth happened the following way. Now, greenhouse gas in the atmosphere, CO2, has a balance. I mean, the content of greenhouse gases is given basically by the balance between the weathering reaction. I'm on camera, so I have to put it up in order to remember. The weathering carbon silicate geochemical cycle, which is basically taking out CO2 from the atmosphere and putting it into rocks like that. Now this is then at some point subducted and the same with the sea floor as Tom told there, the sea floor is young because it's being subducted all the time, and the CO2 will then be outgassed through volcanoes. So this is basically giving a balance, basically giving the content of CO2 in the atmosphere. The balance between the drain and the source here of CO2. Okay. Now, if conditions were such that this balance was imbalanced in some sense, that for instance the rate of volcanic activity went down due to changes in tectonics and so on, the amount of CO2 might drop. And how would that look in my simple model here? I mean, basically, if the amount of CO2 drops, this G factor here, now it's not, just dubbed it not the greenhouse factor here, that's what G is for, this would drop, and basically at some point, sorry, what am I saying here? Now, if CO2 drops, the outgoing radiation becomes more efficient, so the atmosphere becomes more clear, and this curve will rise. So basically, this curve might go through, let's see here, to how does that look? Something like this. Okay, I should have chosen a different color. Now, of course, you can see what happens here is I go through a bifurcation here. This stable fixed point together with this unstable fixed point disappears, and we only have this stable time point left. So to make this more cartoon with the potential, basically what is happening here is basically what's happening is that the potential from looking like that goes through a bifurcation and going from this climb into that climb again. So we are basically jumping into the ice-covered Earth here. Now the ice-covered Earth, basically this will, if you make a more sophisticated model here of the ice cover here, it's actually not unrealistic since sea ice might grow very rapidly. And basically when we hit something like 30-40 degrees latitude, the increase here, say 1 degree latitude, is much more efficiently radiating back from the sun, just from the fact that the latitude is more perpendicular to the direction of the sunlight here than if it was up here. You see, this has less impact than this thing here, and we drop into the ice-covered Earth situation here. Okay, now that with such a severe cooling that probably the only organisms that could live through that would be bacteria or extreme creatures on the bottom of the sea. We do not know to which extent the sea was frozen or basically the thickness of the ice cover, whether this was a few hundred meters or 4 kilometers. So probably, I mean, basically the existence of life through this period tells us that it was not a complete freezing of the now the chairman is rising, so I have to be fast. So now, yeah, the last question is, of course, how do we get out of that? How come we're not in this situation anymore? And the reason is that basically when we get into this glacial climate, the hydrological cycle stops. So we don't have rain anymore. And this here is really only a net reaction. It involves sub-reactions in which water is a part of it. So weathering needs water. So basically we are blocking this part of this cycle. If that is blocked, the outgassing from volcanoes is estimated to be, we could, I think, outgas something like a bar in 20 million years from volcanoes. So that's quite a lot. So basically, what we did we were sitting around in this snowball Earth, waiting for greenhouse gases to overcome the albedo of the ice. So what happened then was, when then CO2 content in the atmosphere was so high that the ice could melt, we had a catastrophic temperature change. I mean, we went from -40, and when we hit 0, I mean, the ice is gone, period, right? Very short time, the ice is gone. But the CO2 is still in the atmosphere, so the temperature rose to +50 degrees. No, from -40 to +50 degrees or something like that. I mean, you need some real extremal guys to go through that. So the idea is that, nothing larger than something like that could live through this, and that's why we only saw real life 600 years ago. So I think I should stop here.
Sorry to take off, it's very interesting. We'll go on for another half an hour, I'm sure. Axel, what's the situation with coffee? Are they going to shut down the canteen if you don't tell them immediately, or do we have questions now?
Yeah, we have questions.
Fine. Please. Questions.
Last thing, last logic. You say the feeding mechanism stops, so might you outgas more?
oh, you don't have gas more. It's just, I mean, you have a sink and a sauce.
The sink stops.
The sink stops, the sauce keeps going in the constant rate. I mean, it doesn't matter if there's ice. Volcanoes will just go through the ice.
How close are you having polar temperatures which are below the freezing point of CO2 under these conditions? If the global mean temperature is -40, then the polar temperature is close to minus.
Isn't it -80?
Minus 80.
Minus 80.
I mean, if you
Then you're
in trouble.
Can I ask a great question? I mean, in the present Earth's atmosphere, the least greenhouse gas effect by far is water.
Yes.
Surely it has some bearing on this. If it cools down, you remove the water vapor.
Yeah. So basically, you have. I mean, this is sort of part of the. I mean, it's a long story. Let me just.
You talk about CO2.
I talk about CO2. Water vapor is by far stronger because it's the most abundant. The thing is, water vapor is part of the system changing all the time. CO2 is not. I mean, it's slow processes going in and out. So you have this basically you have a balance that sets in. I mean, the idea being, of course, that now if you have water evaporate out of the ocean, you get more greenhouse effect from water vapor, and then of course you get a high temperature and you evaporate more water and so on, and you get the runaway greenhouse effect if you evaporate the ocean. So that would be Venus situation. Evaporate the ocean is very thick atmosphere and so on. The other way around is that cool water gets out of the atmosphere and you can cool it even more and you get defreeze, which would be the Mars situation. Now, of course, this sort of positive feedback will always, you have the stone rolling until it hits the bottom, and this is really where we are. So we're always changing out this sort of equilibrium situation. So it's everything from that, but it's right. Water's in there, but water is sort of part of the system.
Well, the problem is that when it's cold, you evaporate the oceans as well, because you lose the water into the eye and the sea.
Yeah.
Because that's only when you get the krill you can have transportation and.
It's about 20 with how it makes time publicly being here.
Oh, that's the same one.
Down for tomorrow. But what you explained was in late.
That's true. No, I mean,
So
maybe,
all the time. And isn't the beginning, isn't the vision that it's wrong, right? Because you start out with 99%, right?
Yeah.
So you don't have change in temperature.
I mean, basically, we're talking about things at different time scales. I mean, this year, I could have asked why we see snow on Earth now. I mean, why couldn't this happen now? The two things change through billions of years. To me, the most appealing type of explanation would be that you have sort of biology being a part. So basically, I mean, the level where plants are almost suffocating, because the CO2 level is as it's. So basically, you could imagine that you have some people wanting plants, taking out CO2, eating it, getting big, but when they take out CO2, it cools, and they don't like it cold. So they stop growing, and that's perfect thermostat. This is basically in the line of Lovelock's Daisy world.
Yeah, I mean, it's normally stated that the composition of the atmosphere is wholly a result of biology.
Yes.
Sorry, that's something to hang on to, I think, is the problem.
But I just want to understand, because as I get your point, your main explanation was that life cannot have been here for a very long time, because the climate is too unstable. So isn't the conclusion that the conditions you started out with were wrong? That something is maybe what you're coming into with the biology, but if it was not
I'm not saying that this. I mean, this is believed to be a right scenario. I mean, this is not believed to be a wrong scenario.
But if this was right scenario, then we'll come up with an unstable climate.
Yeah, a climate that was unstable at some point. Now, the reason that this is not the case now is probably that land masses has moved around. For this weathering thing to occur, basically you need masses to be around the equatorial regions in order for this balance between the weathering and the outgassing to be functional. I mean, it depends on, again, the hydrological side. If you have a big continent, you would probably have the desert in the middle and so on, and all these things.
Yes, but all in all, you would conclude that life would not really have the conditions to be in here long.
Yes. I mean, life, multicellular life, and only external things probably not for that long.
Okay, so
I mean, if you can live through a freezing ocean everywhere, you need to be tough. Right?
Harry has a question.
Yes, I don't think it's on the extremities that survive this. I mean, you know that there's traumatized colonies of German bacteria from 3.5 billion years ago, and they survived this today, and they still grow in Australia, and they were already kind of multicellular systems. It may just be that we just...
They're not elephants.
No, they're not different, but maybe we just don't know how to look for these soft-bodied organisms that may be multicellular.
They're not multicellular, they're collections of cells.
Well, then, I mean, they form things.
Yeah, there's very large numbers of them, yes, but they don't interact.
And they're pretty big.
Are we?
There's a single cell, you say.
Yeah, I think there's single cells that many of
That
them.
was survive, and you're also saying they survive.
That they do. Well, there's lots of arguments about that.
But they collaborate. I mean, you could argue you are just a single cell collection, right?
No, our cells,
People who are cells
our
collaborating.
cells interact.
I mean-
Like the brain connects elements. No, but seriously, coming back to this question really that you raised, or that maybe your starting conditions are wrong. The thing is that when
That's
life
not a
cycle-
maybe, that's a fact.
Well,
I mean, the starting conditions are wrong. I mean, the sun has changed 11%. Period,
Yes, yeah.
finished.
I wasn't thinking
40%,
so much of that. I
too
think
old data.
the
Forget it.
chemical composition, I mean, the chemical composition of the atmosphere, which is, as you point out, is terribly important for this whole balance,
Yeah.
was completely changed when oxygen producing, because the ozone in the upper atmosphere, you know, the thing which is a principal heat, is the reason why the temperature doesn't go like that and then the stratosphere goes like this.
Exactly.
So the whole structure of the atmosphere...
In the stratosphere you have a negative greenhouse effect. I mean,
yes,
this is a long story, and it's, I mean, basically just this snowball Earth story. It's really a question of 4 or 5 snowball Earths that probably were there around between 1 billion years and 600 million years ago. That's one type of dynamics that's been going on. The very long time scale balance CO2 depletion from the atmosphere and all that is sort of climbed at a different time scale. And I mean, this would be more than half an hour. I mean, basically you should think of things on top of each other. I mean, the overall, change from the oxygen catastrophe and all that, which of course changes everything in the environment, is something different.
Wasn't there a period around 750 million years where there was another kind of life, Ediacaran, I think it's called?
Ediacaran,
yes,
which were multicellular life.
Yes, you're right.
Yeah.
It was a bit of a sport, that's to say, a bit of a thing which stands out and worries evolutionary biologists. There's nothing else, but it all happened at 550. You're right.
So maybe we had these jellyfish elephants, jellyfish people, but we don't see them. That's what you're saying.
I mean, am I right in saying, just to clarify this issue about Snowball Earth, that the Snowball Earth scenario was a product of observations by geologists, and this is not a theoretical construction. This is a theory to explain what people have observed. So it's not that the Snowball Earth is something which is cooked up by people making climate models.
Well,
it's a result
to be honest, I mean, you're right. You know, Snowball Earth was a gift to climatologists, but this model was really made as a model to explain glaciation, right? But a glacial interglacial glacier periods, which we've seen for the last 2 million years, it's nothing like this, right? It's not. I mean, if you lived in the tropics, you would hardly notice that it was glacier period, right? So, but anyway.
But Snowball Earth is also what you would call a controversial theorist.
I think it probably is a bit.
I mean, sludge ball, perhaps.
How many snowball events have there been in Earth history?
Like this, I think something like as I said, 4 or 5.
4 or 5.
I mean, I'm not a geologist. This is not my. But more than one, not more than a few.
I would like to point at the situation that the Cambric explosion of multicellular life took place on a quite short time scale. If you say we have only few snowball Earth, there might have been time enough in between to.
Okay, yeah. But this is, I mean, these are pretty close by. Around, a billion to 700 million years ago.
Okay.
So I mean, but of course you're right. Prior to that, something else could have happened.
Okay, the number of few was just at that time.
I mean, there were glaciation or similar situations in the very beginning.
Yeah.
I mean, 4 billion years ago.
Any further questions? Because I'll probably be able to go to coffee. Ja, nej.
The very hard situations in that meeting, it's hardly all organisms that survive something they get from some point of view. Much better conditions, they will explode and you get the conversion of everything from CO2 to oxygen. So that means that all the areas that animals are. And that's basically what you say in the so it's a consequence of this suddenly you change the situation, and at that time available some types of both plants and animals that were ready to take advantage of the possibility fully media, and then that changes the situation. So go back to so you can call it snowball or rockball or whatever you want to call it.
Snowball is a catchy thing.
Yes. But it's probably very snowball. That's like some.
Ja. Okej. Är det med framkast?
Ja. Ja.
Okej. Den är i grunden. Kanske så det kan just ja. Som är där jag kan göra den sen hantera.
Ei tiedä vielä. Täytyy katsoa sitä könttää. En osaa sanoa vielä.
Ja.
Joo.
Ja.